And now I'm going to give you today's plenary speaker, a man who has certainly been an inspiration to me, Michael Caisse.
Thank you, John. Good morning. Are we having fun? I'm having fun. It is so good to be back at a conference seeing faces. Sometimes people will say that, it's kind of a disappointment maybe this particular year. But what we think about disappointments, we also call exceptions disappointments. So we might as well just call this exceptional. This is an exceptional year, right? It's very good. It's an exceptional year. This morning, I want to talk to you about small inspirations. How many of you have tried in the last year and a half to order something and you couldn't get it because some device or chip or something or another wasn't available, and so either it's delayed extra long or quite a few of you, in fact, most of you. Yeah, not a surprise, right? We're having some problems with production. We're having problems getting chips in. And it's hard. It's hard right now, right? And in fact, we're starting to see maybe places where devices exist that we didn't think. Now, most of us already know that there are computer chips, processor chips inside of cars. A standard car has about 50 processors in it. A luxury car has far, far more than that. How many of you work in automotive? You? Yeah, you already know that, and you can tell us the horrors later, okay? Did you see those hands? Go find those out. In CES 2016, Ford announced that they had 150 million lines of code in the F-150 truck. That's mind-boggling to me. Normally we don't think about lines of code as being anything useful to talk about, but this number is so large. In fact, this completely made up graph, fabricated last night, shows the trend of software engineers who found out about the 150 million lines of code, and they're purchasing of F-150s. And you can see it dropped dramatically in 2016. It's amazing, isn't it? Yes, and it continued to decline down. So how many of you have one of those cameras on your doorbell or something in the front of your house? Very few. How many of you have an electronic lock on your front door? About the same. In fact, maybe there was a complete intersection between those two sets. So right afterwards, there's some of us might want to talk to you. We're cautious about things like that, right? We're concerned about that. And why are we concerned about that? Because this is a field we work in, right? We understand what's under the hood, the things that scare us, what frightens us about this stuff day and night. And if you work in an embedded environment, you probably are even more frightened at times. You probably don't have light bulbs that you can control through your phone, right? Things of that sort. Why? Because the S up here in IoT is for security. We all know that. So it's not a surprise to us. Between January and June of this year, Kaspersky measured 100% increase in breaches of Internet of Things. It doubled. That's incredible. Now, doubling of these breaches and the attacks is not something a language in itself is going to fix, but we've all encountered bugs that we know the types of things that the language of C++ helps resolve and helps fix. This one was a surprising one to me. Stovetops were suddenly delayed, the release of initial production of stovetops by 4 months because they couldn't get processors. Have you ever thought about your stovetop having a processor in it? Yeah, me neither. So we take for granted so many things that are around us that have processors in them. The things that we think about as having a processor, microprocessors classically, a computer, whether that's a desktop or a laptop or supercomputers or large servers and server farms, they represent less than 1% of all the processors that are manufactured. It's a very small number of things. Most everything else goes into these devices that are all around us all the time. And we haven't been able to get them. Now, I don't know how many of you have seen this quote. A few of you have. This is startling almost, at least from my point of view of someone who works in this industry and sees different code bases from clients all the time, to be able to say that I can't get a particular device anymore and be able to modify my code base for an automobile and have confidence that at the end it's going to be correct in such a short period of time, that's pretty phenomenal, right? How many of you would like to work on that code base? Nobody else would. This is amazing, right? To be able to modify code and have such confidence in a complex situation where you're talking about embedded systems. Okay, so embedded systems are everywhere, right? We see them wherever we go. They're in medical things, they're in cameras and microphones, transportation bits and pieces. Everything we encounter these days seems to have a microprocessor in it. And that probably, for most of us in this room, somewhat creates worry and concern. I'd like to talk just for a little bit about a few projects that I've worked on in the past. And I'm hoping we can get just a little glimmer of some inspiration out of these and things that they mean. And they're all having to do with smaller items, smaller processing type things. Back in the very early 90s, I worked on bit slice processors, or bit slice systems. I worked at a company that was in the semiconductor manufacturing. And our job as a company was to take photomasks, or our job as a division was to take photomasks and create machines that would take photomasks and inspect them for defects. So when you make a chip, you're going to take and make several layers of your silicon. You're going to go ahead and create several layers, right? We kind of know that. And that process is very much like old-fashioned photography. There's a thing called a photomask that's just like the negative. It's going to get exposed, and as it's exposed with the E-beam, onto the silicon, it will go ahead and there's an emulsion layer and it'll go through this bath and this rinse and an etch and all that stuff, just like you would if you were in photography. If your photomask is wrong, life is bad because you've duplicated that error everywhere. And so you want to make sure it's perfect as can be. So the process of doing that is you take the original design data and you render that in some way and compare that optically to what's on the photomask. And these systems were made to do the rendering part. These were very large racks, and in the racks were these bit slice boards. And what bit slice processing is you can imagine, I want to build a processing unit that is going to perform a task, a very specific task. And to do this, I know optimally, if I had like 3 ALUs and 2 multipliers, a barrel shifter, a couple of different latches in places, some registers over here, that would be the optimal solution. And so you would lay out on the board with discrete devices exactly what you wanted it to look like. Now, some of the cool things about this, in this particular project, is we would lay out these boards, and there were dozens of them, to solve the task that we wanted at hand. And since we controlled the board and we controlled the microcode, we would change the clock speed or the clock width for every instruction to optimize the path lengths. So we could run as efficiently as possible on the board. That allowed us to do what we thought were some really great things very quickly. So From an electrical engineering point of view, when I'm double E, this was beautiful. I loved it, right? It was just like plugging blocks together, solving problems. I stayed on the team, and every team of one, and everybody else went off to work on a new image processing supercomputer with specialized ASICs. And I think they knew what was happening. They knew this was coming down. So the top set of diagrams is, you'll see on the left-hand side, are maybe some basic type of features that you would have. The feature on the right looks just like a rectangle, very nice. Rendering is done with polygons, and that right one, or trapezoids, the right one is awesome. It's just a square, a rectangle. The rectangle is going to be easy to render. And, but on the wafer side, to the far right on that top row, you can see it doesn't actually print the way we wanted it to. The resolution, as things were getting smaller, started causing more and more problems. And then somebody was very clever and decided to use, there were a variety of different techniques, but eventually they came up with this OPC, optical proximity correction. The idea is to create constructive and destructive interference patterns with things and features that you can't print. I want you to take a look at my very nice rectangle that was on the top row and see what happened to it in the middle section. Not nice. It exploded with a whole bunch of different shapes. What used to be a single description of a shape suddenly would become 9, 12, 14, sometimes more trapezoids. So the explosion of data through the system was gigantic. And I was the one left on the project to figure out how to make it work. This was Pentium was coming through the fabs at this time. It was a disaster. I wasn't that long out of college. I didn't know a whole lot about what I was doing, to be quite honest. And I was trying really hard to solve this problem. I was making sure all the clock lengths were as short as possible. The instructions were optimized. Did we use the right parallelism everywhere we possibly could? But you know what saved the day at the end? You all do. What's the way we solve problems? Oh, Moore's Law would be nice. That was the other group. Algorithms. Algorithms are always more efficient to solve than the code, if you can, right? Coming back and searching and looking again at literature that had been published, talking to other people who were in other fields, not in the field that I was in, spending a lot of time with other disciplines helped me realize that solving this problem wasn't going to just make the electrons go differently. There was something more fundamental to solving the problem. And I think this happens to us all the time, right? We think about our silo that we live in and we work in, and we forget that the field of engineering relies on science, it relies on so many different things. We can look around at other disciplines and gather and draw from them to solve a problem that otherwise seemed really difficult because we were so focused and down in the weed. The second thing I want to talk about is this TKA. Probably shouldn't ask. Maybe some of you have had one. The idea is that your knee is falling apart and now you want a new one made out of some other, metal material. And about 15 years ago, I worked on a project where the idea was to take and assist the surgeon by using a device that would tell the pressure balance between the medial and lateral of the cut, and they would be able to then balance using pressure instead of just like the gaps are about the same. And they found that this worked out really well, but they didn't really have a great way to do it. And we went to develop this device. Inside of this is a PSOC with a whole 4K of RAM. And inside of this is the same. And they would they would pair these things up and be able to see a variety of different information. You can imagine that hospitals don't like you broadcasting a bunch of data around about patients, even if it's just the pressure of a need. So suddenly the problem became a little more complicated. We had to solve it in such a way where data was encrypted. Maybe it was, in fact, it was somewhat hidden. It did frequency jumping. It did a whole bunch of weird things in order to try to allow this to pass the FDA approval. And it did it, unfortunately, in only the 4K. Now, I wanted to use C++. Why? Does it need C++? Well, it would allow me to abstract things like state machines. It would allow me to use types to make sure that I didn't pass arguments in the wrong spot. It would let me have more confidence in the final solution that I built. But you know what? Even though we say it, there ends up being languages below C++. And sometimes you can't get the C++ to fit, and you have to use the tool that you have. So unfortunately, the tool that I had was assembly and a little bit of C. It would have been nice if I could have done it in such a way where I could have used C++. And there are a variety of reasons that I couldn't, but at the end of the day, it comes back to this. Engineering's a tool. This company was a weird company. They would hire me. They would literally sit me down in a chair and make me watch medical operations, like surgeries. The first time this happened, we were about 10 minutes into a surgery, and they said, "Oh, do you get queasy?" I'm like, "It's too late if I do, isn't it?" So, yeah, it doesn't matter anymore. But what was it that they thought that I could provide? So interestingly enough, people look at you and I as people who have these tools that somehow you can bring them together to craft something. For the same reason you would go to the blacksmith or the woodworker in the past, because they know how to use tools to solve a problem. You and I know how to use a set of tools which allows us to solve all kinds of problems. It doesn't matter the domain we're in. That's, to me, the exciting part, actually, about engineering. If you were at my talk earlier in the week, I was talking about a project earlier from this year in which we paired up MCU and an FPGA. This is a common solution for us. And it's one that a lot of people will initially balk at. But you know that this is going to be true because you've experienced it yourself. How many of you are super excited about parallel algorithms? Yeah, of course, right? Who would not be super excited about parallel algorithms? What is more naturally parallel than an FPGA? Right? It's just naturally that. You write in a language, if you use like Verilog, for example, you write in something that expresses your intent and lets you do exactly what you want. This particular project, we needed some very particular timing, and it was complex and hard. The device is an Infineon XMC, is the MCU device. It has a whole series of complex capture and compare units and timers that can cascade and do all kinds of really amazing, wonderful things. And to be quite honest, it might have been possible to solve the problem using a bunch of those. Maybe. But it would have been hard. It just was a natural fit in an FPGA that was going to cost me $5. You and I, as engineers, are really bad at a lot of things. And one of the things that we seem to be bad at is estimating things, right? I probably shouldn't say this on stage, but I'm going to anyhow. As far as I can tell, this whole idea of like, we're going to do sprints and stuff is like, finally the engineers said, we drive the boat and we're going to control the company. I don't know. We don't have to say when projects will be done. We don't when's the end date? When are we going to be able to ship? Things like that. I know it's not quite that bad, but we're really bad at estimating, right? That's just something that we're just naturally not good at. You know what's something else that we're naturally not good at? We're not very good at making cost accounting determinations. We're not very good at saying, if I solve this particular problem, it's going to take me probably a week. I can probably solve this problem in a week. And realize that for the life of the production of the thing, if I added that other chip, it would have been like a day of my effort, right? We're not good at that type of thing. But we need to be better, and we need to work as a team to understand how our impact as engineers affect an entire organization. All right, so let's talk about freestanding. Why do I want to talk about freestanding? This is completely selfish. Some of you in the audience are with WG21. The last time I got to talk about freestanding was in San Diego at an evening session that was poorly attended. And who could blame anybody for wanting to go to one more session, right, during the week? I did a poll earlier. I asked, what is freestanding? What is the target for this thing called freestanding? And as you can see, the majority of a whole 49 votes, so that's very statistically interesting, said that it targets without an operating system. Let's not worry exactly what freestanding is. Whether it's the thing that is for things without operating systems, or it's like it is the operating system, or let's not worry about that at the moment. Because what it's trying to target is a classification of a thing. And if we go back and think about what are the principles of C++, what is C++ going to give us? Well, we always talk about don't pay for what you don't use, right? Awesome. No language below. That sounds pretty good. I can write exactly what I want, where I need it. Zero cost abstractions. I like the idea of having an abstraction and not having to pay for it at runtime. I love that. And then from Bjarne's talk, we'll just pull in two more things that he said help guide him along the way. Managing complexity and efficient use of hardware. So let's talk about this list. Don't pay for what you don't use. You don't have to spend a lot of time talking to somebody to find out that that's in the embedded world, that they don't like paying for things that they don't use, which is why the first thing they do is they shut off exceptions in RTTI, right? So if you want to use the language, there would have to be things you would pay for that you don't want to use. No language below. Clearly there's a language below because somehow we have to boot up and get going, right? And we sometimes have to escape it in order to do things we want. Zero cost abstractions. I don't know personally of very few, maybe one or two, people that I can think of in the embedded world who care about compile time. Why? Because generally speaking, we don't have projects that are enormous, right? They take some amount of time and hopefully you're thinking as the compilation's going on. Let's talk about complexity. We can talk for the rest of today about what in the world embedded means. But at one level, we can probably all agree that embedded is about large surface areas. There are a lot of I/O, different types of I/O, things being communicated with and controlled, organized. Inherently, they're complex. And as our systems become more complex or larger, we're dealing with more things, then what's managing them becomes more complex. And then efficient use of hardware, of course, we definitely want that. And I think we have that. So there are a lot of really good questions talking about hosted versus non-hosted. Why do we need freestanding? Why should we have it in the language? We already have this, by the way, this bifurcation of there is part of the specification talks about hosted, and there's another part that talks about a target called non-hosted, all right? So it exists inside of the language. So is there going to be bifurcation? Well, we already have it. That would be the simple, cop-out answer. That's what it would be. But let's think about this a little differently. As we add new features into the language, what do we normally do? We say, steer towards these new features, don't use the old ones. There are reasons that we don't want you to use the old feature anymore. The language just continues to grow and grow, but we guide ourselves into other corners and we guide ourselves into areas in which we make it more narrow, what we're using. It's not so much bifurcation as it is what we're already doing. These sets of features are appropriate for these types of targets, these types of things I want to achieve. User demand. So there's this question about, is there user demand for this? How come we don't hear users clamoring for freestanding? Why not? How many of you have a friend or are in the embedded industry? Don't you love how every spec sheet you get is wrong? I mean, yes, they're 1,200 pages for the processor. And so, yes, there will be errors, right? But it's a pain when it's the power up special function register and the bit was the wrong bit in that one, right? And you're just struggling, why can't I get this thing to work? We're used to struggling with things that aren't necessarily perfect. Okay, I think all industries are that way to some extent, but when you're dealing with hardware, it's really that way all the time, it seems. It's this constant struggle of what's not working now and why. And so there might not be user demand because we're used to all these wacky tools and just working around problems all the time. There could also be user demand and we're just not listening to it properly. That might be it too. I think when I talk to people, they want a better language. They want a language that will cause them to program in a way, or allow them to program in a way in which they're going to make fewer errors. There are a few, right? There are a few of those people still there who are the machismo, I want to use my C and do anything I want. I am never going to tell you what parameters will come into the argument list because I can figure it out later. There's a group of those people. But I think the community wants to not write bugs just as much as you don't want the medical device that you're using to have the arguments swapped in the argument list, right? I think generally that's true. I know quite a few groups right now that are moving to Rust, that are in the embedded world. And they're moving to Rust not because they inherently think Rust is a better language. They're moving to Rust because the Rust community is taking them serious. They're actually looking at their problems, they're asking for solutions, they're taking their feedback. It's a community that seems to understand that the other more than 99% of devices that are running around might be important as a target. So, regardless of what freestanding means, I think the biggest value to WG21 is simply allowing this question to be on the checklist. What is the impact of the feature or the change that's coming through in this paper to non-hosted targets? If we just asked that, like we asked so many other questions on our checklist, we would have answers about maybe, and it's perfectly fine if the answer is, this just doesn't work on non-hosted. It's okay. But maybe if we think about it a little harder, we would have a solution. Here's an example. All right. Imagine that you wanted to add a new feature, a new algorithm to the standard, in particular that is really associated with ranges. And you know that the best way to describe this thing is to use coroutines, because that's what would make sense as you described it. And coroutines is just a feature in the language, just like the spaceship operator, right? So we should be able to just describe the feature that way. But coroutines requires allocation. It might be optimized away, but the feature requires allocation. And the number of people I've spoken to who don't want to figure out how to implement the allocator so that they can run coroutines on their embedded device is amazing. And I'm not talking about small companies. I'm talking about companies that are in the top 5 who have more than enough money to devote to this if they wanted to. And they're just like, nah, we won't use coroutines. So now imagine that you brought that feature forward to the standard. And they said, yeah, let's just mark that as coroutines. You've now eliminated the non-hosted group of people from utilizing it. They're just not going to use it, right? And because we don't have this question on our checklist, we're not making that determination. We're not thinking about what that impact is on that whole group of people. Here's another one. This came up in San Diego meeting. Peter Demov had put together this paper about error category message, and he had suggested that we go ahead and create a variation of it that didn't require allocation, so non-allocating version of this. Perfect. I was very excited about this. It got shot down immediately because of ABI concerns, but that's not the point I want to make. The point I want to make is if something was in our process early on, so we simply asked ourselves the question, how does this impact non-hosted platforms? We might have made the change early on as it came in and said, oh, well, this is almost free. Let's just add this in so that a whole class of users could utilize this capability. So what I think would be useful is that for that more than 99% of processors, IEEE estimates that it's more than 100 times the amount of code that exists across all code bases. That whole group of people somehow are represented in our checklist by just simply saying, how does this feature impact non-hosted? I think it would go a far way. All right. I doubt that last part inspired any of you. But I hope if you're in WG21 or participate in it, that you give a little bit of thought about the usefulness of freestanding is to improve the process along the way. I haven't been very involved in the last couple of years, but I'm hoping that's changing here starting next month. And so at least I will be clanging that bell a lot. So what inspires you? What is it that put you in this seat today or put you out there watching this video? Why are you interested in technology? Why do you do this thing that you do? I want to share a little bit of my story, not because I think my story is special in any way. I think it's probably going to be just like your stories also. We will have commonality, but to remind you of what it was so that you can pull on those experiences and those memories again to inspire other people. We are inspired by the things we encounter and the people we meet. If you didn't already know when I grew up, you'll know now because that's some pretty classy looking 70s gear there. My grandfather was the 10th child of 11. He was a Depression baby, grew up in the Great Depression, and his parents, both parents, died of typhoid when he was very young. He and his younger siblings were not very useful on the farm, and so the older siblings took them and shipped them away to families that would be able to care for them and feed them. He grew up and eventually moved to California, became a barber. But more important to me, he became a magician. He loved magic. He would pick me up and we'd go to coffee and donuts, and he would show me these magic tricks. He would take me to magic shows. It was amazing. I was always just like, how did he do that? That's so cool. I wish I could do that. As I sipped my coffee, which was just hot chocolate, and acting cool like him. In 1976, I was told I had to go to summer school. And as a kid of 7 years old, I couldn't imagine anything worse. Personally, I wanted to play in the creek with all the other kids. So this was going to be a disaster. My grandfather told me it would be fine because I would get to take science classes if I wanted to. And I want you to know, science classes and math classes belonged in the exact same room, in the same corner. And it wasn't too long before that I was told by a math teacher that I wouldn't be able to become the astronaut that I desired because I couldn't memorize my multiplication tables. So, I don't know, it didn't sound very promising to me. But he took another stab at it. And he said that that science is actually the true magic. Taking science classes is learning all about magic. Well, that was my hook. And I was completely like, yes, that's what I want to do. I want to learn about magic. So I was all excited about summer school, and I ended up having a really great summer school teacher. And so that seed was really taking root, and I thought science might be the thing. It's cool. The following year, I got a 150-in-1 electronic project kit. Any of you have like a variation of this? They're so cool. I absolutely loved it. I just ate it up. It was the best thing I'd ever seen. But the problem was my family knew nobody who knew anything about electronics. So I became the in-house expert. I learned very quickly that electronic parts also run off of magic. Magic smoke. And when you let the magic smoke out, they didn't work anymore. I stored up all of my allowance. I would go to Radio Shack. I would buy devices off that back wall. I had no idea what they did, but they had cool names. I'd bring them home. I'd read the spec sheets. I'd try to figure out what in the world they were. I'd let the magic smoke out of them, and then I'd repeat. But when I was 12, something absolutely incredible happened. This company decided that it was going to come to our school and teach about programming. And somehow, I was selected to join that group. My guess is it was because I was a completely annoying kid, and they didn't want me in class. What made me annoying was I had read this math problem in Scientific America. It was a word problem. And I couldn't figure out how to solve it. I wanted to solve it so badly. I asked every possible teacher in the school, how do I solve this? And unfortunately, not one of the elementary school teachers there could help me. They had no idea how to solve it either. But I would continue to ask every week as if maybe they would go home and study up and figure it out. As an adult, I can now tell you how ridiculous that sounds. But at the time, I thought that's what they were going to do. So the programming class was amazing, and it used a language that later on I would learn was Logo. But it wasn't just drawing graphics on the screen. In front of us were these flatbed plotters. So the plotter itself would go and grab a pen and it would draw the thing. And suddenly, it wasn't a rabbit hole, it was like a whole new universe. I suddenly understood that I could take mechanical things and electronic things and this thing called software, and pretty soon all of it could be glued together into something larger, and my mind just went wild. And I was like, fine, I can't be an astronaut because I don't know my multiplication tables, but I'm going to tell you, I'm going to learn how to play with robots. I'm going to grow up and I'm going to work with robots. That totally set me down this path. That same year, my best friend got a Commodore PET. I mean, let me tell you, when you just finished, you have never even seen a computer before, right? And you just finished taking this class, and then your best friend has a PET, you're spending the night there every night. It had a 6502 and a whole 4K of RAM. It was so incredible. We had no idea what we were doing. We played the weather game an awful lot, though. So that following year, I worked really hard, I saved money, and I had enough to buy half of a Commodore 64. It ends up that half of a Commodore 64 is not very useful. And at the ripe old age of 13, I was still living at home, and my parents were kind enough to buy the other half, and so we just put those two together and kept it in my room. As I entered into high school, with my word problem in my hand, quite literally, my first day of high school, I found the teacher that taught whatever the highest level of math was. They said, it's called calculus. And I found him and I said, I have this math problem and I don't know how to solve this word problem. And he walked me on over to a blackboard and he showed me exactly how to solve it. And I was like, wow, it was that easy the whole time. And Dick Noble ended up becoming probably one of my best friends for life and continues to, in fact, inspire me today. People inspire people. Our interactions with one another and other people, that's what inspires one another. When I got to college, I was the president of our IEEE chapter for a couple of years. And one of the things I had to do in that position was travel around to elementary schools and show them what an engineer was during engineering week. As if somebody in college would have any idea what it was like to be an engineer. But I could fake it just as well as the next person. I'd bring canisters of very cold gas and put flowers in them and crack them on the floor or whatever else I could figure out, right? To keep the kids interested. And you know what I learned in that process? They were excited. I was excited. And I was doing the exact same thing that everybody else had done to me growing up. I was like, wow, this is so cool. I could talk about the things that I love with a group of people who are being inspired to perhaps move down that route or explore technology in a way they hadn't thought. I was giving back that same thing that I had taken for myself. It's important as a community that we do the same thing. You might be involved in that initial seed where you love that group or that age or those people who are just now coming to the process. You're introducing it to them for the first time. Or perhaps you're that person who the next stage is the rough one. Are they going to make it through or not? Are they going to be able to have the support along the way? And all of us can make the environment better because we're already here, so when they arrive, this is a great place for them to be. There are some things that I've encountered over the years. And again, these aren't necessarily super special, but hopefully they give you some idea of things that you can take and talk about and we can share some ideas about how to inspire other people. How many of you have heard of Minecraft? That's a surprise, everybody. Okay, how many of you have used Minecraft? Nearly the same amount. Minecraft is pretty amazing. Minecraft is this world, right, that we can build things in. When Simon was 6 years old, a friend of his 16-year-old sister would come on over and play with him with Legos on the floor. I'm pretty certain Mason came over not just to play Legos with Simon, but that's a different story. The two of them would sit on the floor for a long time, building, creating things. And then one day, Mason introduced Simon to Mindstorm. To say the least, Simon was inspired by Mindstorm. It was very cool. He would build ancient wonders. He would build these views of things that he was learning in history. Every subject in school became a thing that had to be recreated in Mindstorm. It was really neat. There were fantastic buildings. There were secret layers. His mind could explore. But the interesting thing about Minecraft is he would be able to make these cool contraptions that did things. Because it's not just static blocks that you can stack on one another. There's an active component to it too. One of the things he made when he was 10 on the mobile version was a 3D printer. It coincided with us getting a 3D printer at the house. And he would open up a chest and describe inside of it, or on a thing, he would describe with blocks what the thing is that he wanted to print. He would lay down the different color blocks. He'd press the button and come back a little bit later, and it had laid all the blocks down. Now that code is long gone, but if you bribe Simon with coffee, he'll do something again for you. And so this last week, he put it back together on desktop for me and made this video. So this is not exactly the same thing, but it's printing. It's a 3D printer, and it's printing with these blocks using the same type of mechanisms. So how does this work? Well, there's a thing called redstone that we can kind of think about as traces throughout. They allow us to send signals around. And there are the elements and basic building blocks of logic. And you can take that logic and you can put it together in different ways to form larger bits and pieces of logic. You can create flip-flops. Well, if you can create flip-flops, you can create memory. And pretty soon, in fact, community people have created small processors using redstone in Minecraft. It's really kind of like the mind is the end limit. And as Simon was talking about how it worked to me and telling me more and more about this, I was like, wow, this is a lot like the electrical stuff we talk about. This is a lot like the electronics things that we do. This is really cool. And then we started spending more time together talking about it. And he started showing me how it worked. And the next thing you know, I was like, this is actually just like gate logic in an FPGA. So at the young age of 11, I believe, was his first introduction to FPGAs. Because you know what? The leap from an FPGA and the way the logic works from this was almost zero. He already had a mental model of how all of this went together and how it worked, what it did. He just had different names for it. One of us had to adjust the names, and I'm old. So Simon got to adjust. When you pair in Minecraft all these gizmos with actuators and whatnot, and then you realize that that just translates directly into our world of maybe FPGAs and learning Verilog and whatnot. The translation is easy, and you can excite one another because now we've got robots moving around or detectors working, and there was like this exact move between it. So our 3D print is almost over here. Is that an R? It is, isn't it? Is that an R in a gear circle? Is that the Rust logo? Oh my goodness. All right, well, Simon might be looking for somebody to eat dinner with tonight. So part of the way that this works in Minecraft is you find the peculiarities of different components and you figure out how to put those together in such a way that probably somebody didn't intend you to put them together with. Simon's quote is, "One of the most fun things about Redstone is exploiting new features when they come out." So maybe Minecraft isn't just like a good segue into talking about FPGA and logic and Verilog, but perhaps it's a gateway drug for C++. All right. So this is junior engineering group number 2. This group was with us for 3 years. How we did this is we would take family members, in this case it's Simon, and friends, and we would invite them over twice a week, and we would talk about things, mechanical things, electronics, software, engineering things in general, interesting math stuff, how to put it together, and figure out, was there something for each of the kids that kind of resonated? It will be different. Not everybody is going to be excited about software. Not everybody's going to be excited about the mechanics. And we would work through different problems and solve different things along the way. I have friends who've done this with family members and family members' kids, and it's worked out really well. It's a lot of fun. They would design things inside maybe SketchUp and then 3D print it, and then they would first, of course, draw it out by hand and learn about different diagrams and ways to go. They would take programming courses online, and then we would help them with that and figure out how to actually get that onto hardware. They would learn how to use equipment and be able to visualize stuff that's going on with electronics. The idea was just to expose, see where they got excited, continue to move that on to the next level so they continue to be excited about it. The picture in the lower right, I want to draw your attention to that for a moment. That boy who's sitting in the middle with that book, that's my probability problems book. It's just a bunch of like probability questions for fun brain teasers. 50 probability problems or something like that it's called. It would sit there on the coffee table. He would grab that book every week. He ate it up. He loved it. It was crazy. He's not very old. I think he might be 10 in that picture. He loved that book. So we ended up doing things having to do with math also with him because he just kind of like ate it up. I don't know if anybody ever became a great engineer out of there or excited about everything. Actually, that's not true. I know some of the kids walked away with that. But what I can tell you is all of them figured out the proper programmer posture. So that was good to learn. When my oldest daughter graduated from UC San Diego, she took a gap year and volunteered her time with a group called City Year. It's a subgroup of the AmeriCorps. And they work with Title I schools. And she was volunteering at the school or in the organization and working at a particular school. And she came to me one day and said, we have 2 7th grade girls who want to start a robot club. So that, in case you don't know, that's like the soft spot in my heart right there. I'm like, we're going to figure out how to start a robot club. It's going to be awesome. And unfortunately, there were some challenges to the robot club and starting it. The first is that it was a lunchtime club, which meant we had 20 minutes. So we had to figure out how to do something in 20 minutes. The other problem was all of the Lego robot kits that we thought were available were lost. And they had no money to buy more. So we thought, maybe there's a way that we can do something. We can put something together that would work. It was at the exact same time that I happened to be at a CppCon, and Sarah Chip was there showing off her Joule bots. Were any of you there and sat in that thing? They were amazing. And I don't know, if your name is Sarah Chip, I don't know how you can't be amazing, to be quite honest. But Sarah is very inspirational. She had people up there talking about it. That's my friend Nicole up there. That's my wrist hanging out. She and I became Joule bot bracelet friends. And these things, as they got closer, they had Bluetooth in them. We could send secret light messages to each other, and they would know when we were in the area of each other, and they would light up differently, and you could program them however you want. They had an Arduino on them. And I thought, that's really cool. Sarah ran a class. People from the community came in. I watched how she did that and the style, and it was inspiring to me and completely inspiring to every single person in that room, regardless of their age. And I thought, wow, if we could figure out how to take that into the classroom, that would be really cool. So, for Christmas, everybody got, in the engineering group, got these boxes that you can make into robots. The box was the chassis, and they had little Arduinos in them, something called a red stick. I thought, great, because this group that I already have hanging out with me a couple times a week, they're going to be my guinea pigs. They're going to figure out how to make this whole thing work. Pretty soon, of course, the boxes broke, and then they were 3D printing things because, to be quite honest, some of them really just wanted to use the 3D printer all the time and didn't care about anything else. And so we got different variations of this. But the whole end result was disappointment. Because when you show up at a school saying, I really want to install this software on your computers, they just laugh at you. And they laughed for two reasons. One, there wasn't really much to install it on, and the other was because they were Chromebooks, and the other were the ones that we could do any installation on would just never happen. So it was back to the drawing board. So we tried the Raspberry Pi bots. We took Raspberry Pis, we attached them to bots, we hooked up H-bridges and controlled motors. And this at first seemed like it was going to be great because we had HDMI displays that were inside of a little kit you would open up, and the HDMI display was there, and it had a keyboard that would just come out that was wireless and had a little trackpad built into it. And you just plug the whole thing in and just go. I'm like, yes, it's self-contained. And it ends up that the first thing the kids did is they made remote control cars out of them. Not what I was expecting or wanting, but whatever. It was fun, but it was too complex. It was way too complex for what we needed. And then I discovered the microbit. So the microbit ends up being this godsend for this type of environment. It has tons and tons of capabilities. The BBC put it together for learning. They have lots of resources to help support you along the way. But best of all, you plug this thing into a laptop through a USB cable, and it just looks like a USB drive. You drag and drop on your file that it's going to run, and it's done. There's nothing to install. There's nothing magic to make it work. Which brings us to the other cool thing about it. It uses MakeCode. It's all online. And I could either graphically put something together, which is when you're working with younger people, syntax and how you speak the particular language is really not important. Putting the logic together and understanding how the logic works graphically is just fine. And you can do very complex things that way. And so MakeCode allows us to do both that with graphics, Python, JavaScript. There's also a C++ way that you can go with microbit. So very capable, and we put these robots together instead. And these robots ended up being a huge hit. They were able to use them and continue on from where they left off within their 20 minutes. The goal by the end of the class was a line following robot that had lines that moved both left and right. And so by the end of the year, everybody got it figured out. And it was totally awesome to watch. In fact, the first time they got one to go, all it did was this. It just spun around. And you can't hear the audio of this, but right now, the kid yells when he notices it. He goes, "Oh, yeah!" And you just see and feel the excitement in the room because they did something over here in the computer, and over here the thing moved around. They affected their world. So it ends up that I love microbits now. They're my favorite thing in the whole world. I use them for everything. And this is a picture from our last meetup before the shutdown to 2020, March 2020. And I said, we're going to go ahead and we're going to have a challenge. So we're going to have a coding challenge. Come, we'll have our normal talk. But when you first arrive, you're going to get put into teams, and then you'll get a coding challenge. It ends up that nobody who showed up knew how to use microbit except for this young man. His mom's a software engineer, comes to our meetups on a regular basis, and she sent me an email saying, "Hey, can I bring my son to the meetup? He loves microbit." And actually, sorry, at the time it was like he loved Scratch. He knew how to use Scratch, and he loved Scratch. Would this be enough similar? And I said, it would be exactly similar. It ended up like, he blew all the adults away, of course. His stuff was working before anybody else. When we moved into the session, and I believe that evening we were talking about CUDA. Somebody's giving a presentation on CUDA. He could care less about CUDA. He sat there at the table, continued to make his microbit do other cool and interesting things. And when he left, all he wanted to do was play with all the electronic equipment in the lab, and we sent him away with a microbit robot. And we occasionally get updates still saying how wonderful it is. I throw this out because you probably belong to a meetup or have a meetup also. I wish I thought of this idea, but I didn't. Bridget thought of the idea. And from now on, when we get live in-person meetups going again, I'm going to have one a month that involves microbits, to be quite honest, and some challenge, and invite people to bring youngsters so that they can work on the challenge with the rest of us and then maybe move over to another area of the office and deal with that while we're talking about boring junk. Okay, so this is not like the one that's at the school, but it's like the one that's at the school. This is a chassis that comes with through the microbot, through SparkFun. And I think we should give this away to one of you. What do you think? So the way we're going to do this is we're going to pick a section, and then we're going to pick a row, and then we're going to pick a number across. And so if you're not in this area, in the seats here, you'll want to do that. And we're going to just use modulo type math so that we can get it right eventually, all right? So we'll just set this here. This is another thing that if you tell Simon that you'll give him food, he'll do other stuff for you. So he programmed our little microbit to hopefully not run off the stage. And it's going to actually make the determination here in a minute of who's going to win it. All right? Sound good? All right. So, how do you get involved with something? It doesn't have to be grandiose. It could just be you and one other person, right? Our influence typically is with other individuals and getting involved with other individuals. So many ways to get involved and to do things. I've given a couple ideas. I hope that maybe on Discord, if you're in the live audience or on the online audience, that we can talk about other ways to get involved in community and inspire people. I have this email address if you'd like to send something there. I'm eventually going to put out a site that has ideas for community and a community set of ideas. So if you're interested in that and watching this later, send an email there and we'll take care of that. Everything that I've talked about is somewhat US-centric, but I did bounce these ideas off of people in Germany, at least. And there are ways to get involved with schools there and the ways of get involved with different clubs there. There's probably something in your area that you can get involved with. And what I hope is that we as a community here at this conference can maybe brainstorm some ideas to figure out how to inspire future technologists to not just start, but stay with it through those harder years. All right. So to do this, I need a volunteer to help. Vishal, come on up. All right. I didn't set this up well enough to have a camera. Come on up the stage if you like. Okay. How do we want to do this first? Are we going to go A, B, or are we going to go A, B? Which one do you want to be A?
How about A?
Should that one be A?
Oh, A, B.
A, B. All right, we got the A, B part. Pick that, push that button, and then tell us, what does it say?
B.
B. Okay, we're in this group. Woo! Come on over here. Oh. All right, we got to get in the right spot here. All right. Press this button, and we're going to figure out these numbers. They're zero-based, I'm told.
Okay.
But you don't know. All right, here we go. Let it go. Press it again. Let it go. Row 1. Seat. I have no idea what that said. Was that a 6? Okay. All right, row 1, seat 6. Are we gonna count from left to right? Don't look. Are we counting from left to right? No, not yes. It's a.
Okay. So, 1.
Okay, all right. 0, 1, 2, 3, 4, 5, 6. This gentleman right here with the coffee cup. All right. Congratulations. We got some more servos that go with that. We'll get that to you here soon. Thank you, Vishal. Woo! Oh, I love giving stuff away. Anybody have on a Boostash shirt today? No? All right. When we got on the airplane to Denver, this very tall guy came on who was very hip, I have to say, had this black t-shirt on. And it said, "Be inspired." Simon told me I couldn't actually offer to buy the shirt from him. But I was really tempted. Be inspired. I loved it, and it was kind of like awesome because I'm going to go and give a talk on this. How cool is that? How many of you seen this meme? How it started, how it's going. All right, how it started. Let me help you. How it started picture underneath there. What you see is you see Michael, age 12, and he's sitting there at a computer, and there's a flatbed plotter in front of him. And it's moving around with a pin, and it's going off quickly, and it's changing and grabbing another pin. And then you notice on the side of it, it says HP, because the biggest employer in our area, other than the wine country, was Hewlett-Packard. And it was Hewlett-Packard Instruments. They built instruments to do measurements and things of that sort, oscilloscopes and logic analyzers. And eventually that got spun off and became Agilent, and then it became Keysight. And all right, woo, that's right. Keysight, ah! Okay. So now let's picture what's under how is it going. Picture Michael again. 5 years younger. I hope I have a little less gray. I don't know, maybe I have the same gray. And I'm standing in front of a room, and there's a set of tables. They're kind of set in a U shape. It's a fairly decent sized room. And there are a bunch of people there. Michael's up in the front, and he's teaching C++. And these students are another group of students. Some of their colleagues in another site in another state had been trained previously, and some of their other colleagues have been trained actually at a pre-conference at or at CppCon, not long before that. And if you look carefully, there's actually a tomato on top of the projector because somebody brought me a tomato instead of an apple. That was weird. And each of them have badges. And if you look very carefully on the badge, there's a company name. And it says Keysight. So many years later, almost 40 years later, after they taught me how to program, I'm standing in front of a room of a bunch of people at Keysight teaching them how to program. Is that crazy? The impact we have on people and the way we inspire them when they're young walks through the rest of their life, right? And it allows them to make impacts on other people. So one of the young girls who wanted to start the robot class, Hadia, stayed with it. The other young girl decided that she really liked mechanical things, and we didn't really have a way to do 3D printing there. Hadia sent this message to Karine last week. She said, I'm going to graduate this year, and I'm going to go to a 4-year college. And not only that, I'm going to study computer science and computer engineering. Now, she isn't sure how maybe all that financial aid stuff's going to work, so I'm going to let one of you talk to Hadia. But that's how it's going. Inspire and be inspired. Thank you. We have a few minutes, it looks like, for questions. Yeah, go ahead and use the mic if you'd like.
Hey, this is not much of a question, but a comment. So first of all, very, very great talk.
Thank you.
I was very surprised that you actually mentioned the subject of coroutines and freestanding together. And one of the things that you said is like, hey, so what if we introduce this generator in the standard and it would not support freestanding, right? And what I want to say is that I really want to answer it now, whether it's going to work or not. I mean, coroutines in freestanding. But I want to invite you and anybody who wonders about it to talk at 2 p.m. in Valley 1, and just we'll find out whether coroutines are going to work in freestanding or not.
All right.
Thank you so much.
Here we go. All right. Thank you for your time today. And find me in the hallway. Let's talk about robots.